An 80% cache miss rate on a single viral video collapsed the origin server and took down the entire site. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design YouTube. Design YouTube is a system design exercise that forces you to reason about every tier of a modern distributed system. It's not about building a video player. It's about keeping the pipeline running when 500 hours of video arrive every minute and 2 billion people expect sub-2-second loads. The upload pipeline must accept unreliable clients. YouTube uses chunked upload with resumable support. The client splits the video into 5 MB chunks, sends each with a session ID and offset. The upload service writes each chunk to blob storage and records progress in Retries. This is the first point of failure. If it goes down, no new content enters the system. Here's a sample configuration for the upload service. It enables chunked upload with 5 MB chunks and resumable support. The service depends on a metadata database and a transcoding queue. Always store the uploaded chunk in blob storage before writing metadata, never the reverse order. Once a video is stored, it must be transcoded into dozens of formats. YouTube splits the video into short segments, e.g., 6-second GOPs, transcodes them in parallel across a pool of workers, then merges the outputs. This is mandatory for large videos to avoid hours of serial processing. YouTube serves most video bytes from its content delivery network. When a user hits play, the player requests segments sequentially. To avoid cache stampedes on hot videos, YouTube uses request collapsing. Only one request per segment goes to the origin, others wait. Pre-positioning predicted popular content reduces cache miss rate by 80%. YouTube's metadata layer stores video info, user profiles, watch history, and comments. It uses horizontally sharded MySQL with a distributed cache to absorb reads. Writes go through a write-back cache to handle spikes. Consistency is traded for availability. A comment may not appear for a few seconds. YouTube's recommendation system uses a 2-tower neural network. One tower encodes user signals into a vector, the other encodes video features. The dot product scores relevance. At serving time, it retrieves top candidates from a nearest neighbor index, then re-ranks with a deep model. This balances latency and accuracy. Every millisecond of rebuffering bleeds user retention. YouTube uses a client-side buffer that adapts to throughput and playback speed. The algorithm tracks moving average download speed and adjusts chunk size requests. If bandwidth drops, it degrades quality per segment instead of stalling. Here's a Python implementation of an adaptive buffer. It tracks download speeds and decides when to prefetch. The buffer maintains a target duration and a minimum. If the buffer is below target but above minimum, it prefetches. This prevents both underrun and memory pressure on low-end devices. Thumbnails are the silent killer. Every video load triggers 4.8 thumbnail requests. YouTube splits thumbnails into a hot tier in Retries for the top 1% of videos and a cold tier in Object Store. On miss, a background job warms the cache from Content Delivery Network access logs. This cuts P99 latency from 200 ms to 8 ms. This code shows a thumbnail cache sharded by video ID hash. It uses Retries with a TTL of 1 hour. The shard key includes a shard number to distribute load. On get, it returns the image bytes or none. This design handles the massive thumbnail request rate. This is the same issue we highlighted at the start. Here's exactly why that happened. A single viral video became a hot key. Every viewer requested the same segment at the same time. Edge caches had an 80% miss rate because the video was new and not prepositioned. The origin server collapsed, and cache fill requests overwhelmed the metadata store, causing uploads to time out and the site to become partially unavailable. The fix involved 3 changes. 1. Deployed request collapsing, only one thread per video segment fetches from origin, others wait on a promise. 2. Added a local bloom filter per edge node to deduplicate requests. 3. Implemented a per-video circuit breaker that drops new requests after a threshold and returns a cached placeholder. This prevents cache fill storms and protects the origin. Without request collapsing, every concurrent request for the same segment hits the origin simultaneously. This can overwhelm the origin and metadata DB, causing cascading failures. Always implement collapsing at every cache layer. Transcoding a long video serially can take hours. Users see processing indefinitely and may abandon the upload. Instead, segment the video and transcode in parallel across workers. Serving video bytes from origin is expensive. Without multi-content delivery network and aggressive caching, egress costs can explode. Negotiate direct peering, use multiple CDNs, and set per-video egress quotas. The article's adaptive buffer uses Asyncio, sleep with a computed duration that may not reflect real network conditions. In Python 3.11+, Asyncio task should use Asyncio, create task for concurrent fetches, and the buffer logic should handle cancellation on player stop. Also, the thumbnail cache uses MD5, which is not FIPS compliant. Consider SHA-256 for production. The article mentions request collapsing, but does not show code. Here is a concrete implementation using Asyncio locks to ensure only one fetch per segment key. The article mentions retries for transcoding jobs, but does not warn about idempotency. If a job fails after partially writing output segments, retrying may produce duplicate or corrupted segments. Always use unique job IDs and ensure output writes are atomic, e.g., write to temporary path, then rename. When uploads fail, use these commands to locate the bottleneck. Check the HTTP response code, server logs, object store status, and upload service logs. This helps identify whether the issue is client-side, network, or server-side. Let's run through some common interview questions. How to upload 1 GB video from mobile? Chunked upload with resumable support, 5 MB chunks, session ID and Retries. Design transcoding for 500 HRS/min. Segment videos, parallel transcoding via message queue, GPU-CPU workers. How does recommendation retrieve candidates? 2-stage, retrieval via nearest neighbor index, then deep ranking. And a few frequently asked questions. What is transcoding? Converts video to multiple resolutions codecs for different devices and network conditions. How does YouTube prevent cache stampedes? Request collapsing, prepositioning, per-video rate limits, circuit breakers. What database does YouTube use? Sharded MySQL Vitas with memcached cache, Bigtable for watch history. YouTube's architecture is a multi-layered pipeline. Hotkeys and cache stampedes are the most dangerous failure patterns. Use segmented processing for parallelism. The recommendation system uses a 2-stage cascade. Metadata stores must be sharded and cached aggressively. Ready to go deeper? Up next, design WhatsApp, then design Uber, then design Google Search. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.